Scott needs very little introduction. He has been like, messing around with all aspects of internet for a long time. And his latest one being one of the leading forces in the name data networking initiative. So Scott, over to you for your viewpoint.
So what I want to talk about is the once and future internet. And it's really a tale of two quotes. And in this, I need to say that I'm here under completely false pretenses in that I have absolutely no insight into the future. I therefore will make no predictions about how the future will unfold. Instead, I'm going to address a very simple question. And that question is, how might the internet evolve? And here I'm going to focus very much on the technical issues. I understand that the social issues are extremely important. I just don't think I have anything to say. I share Henning's concern that democracy is at stake and how the internet will be shaped by the result of that outcome. But I'm really going to focus on how the internet might evolve. And when thinking about this, we must make two important distinctions: means versus ends, and dogma versus reality. And for means versus ends, the technologies, which are really the means, they're going to change. Whether that's going to be 10G or everything's programmable, or we're going to have tachyon links. We all know that the technology is going to be very different. But it's important to recognize that we can't conclude that just because we have very different technologies, that the internet will change. Because the basic internet offering, which I consider the ends, has remained largely unchanged despite massive technological changes, 7 or 8 orders of magnitude. And if you listen to people who think about these things, they expect that the rate of technology change is actually slowing down, not speeding up. So we actually have to think carefully about what the ends, much more than the means, not how the internet will be built, but what it's really doing. So what I want to ask is this fundamental question of sort of what service will the future internet offer? And I'm driven in this by a quote by William Gibson, who's a speculative fiction writer. And his comment is, the future is already here. It's just not evenly distributed. And this comes out of a recognition that it takes a long time for technology to disseminate throughout a society. And so if we're talking 20 or 30 or 40, maybe even 50 years out, chances are the seeds of what will be prevalent at 50 are already starting to germinate in the world today. And so if we're going to look at what things that are already here, it's important to separate the dogma from the reality of the internet. And here the dogma is the internet only delivers packets, it's best effort delivery, it's the basic abstraction. This is the architecture we've always had. It's likely to be the architecture we always will have. And the reality is that the private networks run by clouds and also content providers, but I'm just going to refer to them as clouds, they do more than just basic packet delivery. They do this in-network processing in their points of presence. They have flow termination, they have caching, they have load balancing, and this significantly improves latency and reliability. That is, the service you get in a cloud network is just better than what you get in the public internet because of this in-network processing. And so the simple claim that I'm making in this talk is this should be the future internet. That is, this is the thing that's germinating today. It's proven to be feasible and valuable at scale with real customers, but it's only available in these private networks. It's being done in an ad hoc and proprietary manner. Every cloud does it their own way. And in the limited manner, it's not just that it's only available in private networks, but because they can't assume that clients are changing, there are only certain kinds of services that they can offer. So this is a perfect example of that notion of not evenly distributed. And I would say, I would add to that the phrase, and not fully mature, that it is here with us today, but it's not been fully developed. And so I think our challenge is to turn this into a coherent architecture, to enable it to become the future internet. And I say that because the alternative isn't pretty. In my last slide, I will discuss, what happens if we don't. But, the alternative isn't pretty. So the second quote in this talk is attributed to Peter Drucker, but actually Theodore Hook said it back in the 1800s. The best way to predict the future is to create it. And I want to make that clear. This is driving because actually, in keeping with this quote, this talk is not predicting some inevitable future, but about what we should make happen. That is, I'm not gazing into a crystal ball and seeing what emerges. This is a call to action to make this to be the outcome, because I think the alternatives are worse. So the rest of the question, much like a Seder, is organized around 4 questions. So 1, why is the internet so hard to change? How can we overcome this barrier? What would this new internet look like? And given all the failures we've had of trying to change the internet, and when I say change the internet, I really mean its core architecture. Why is now different? And now the work that's going to follow is joint work with many collaborators. We wrote a CCR editorial with 18 authors, 2 of whom are here today, Jen and David. And there's a core design team that's trying to push this to make it a reality. Arvind Krishnamurthy, James McCauley, Urjit Panda, and myself. So getting back to the first question, why is the internet so hard to change? Well, it's because the layer 3 has 2 roles in the architecture. It allows all L2 networks to interconnect. That's what it was designed for. So it must be deployed in every router. That is the definition of a router. It's connecting to L2 networks. And it's almost impossible, because of its widespread deployment in these things that must be very efficient, it's almost impossible to make significant change, both now and in the future. There's no reason that that's going to change. So L2 is very hard to change. I mean, L3 is very hard to change. But it provides the service model to host. That is, IP's best effort packet delivery is what everything on the host has to be built on. So it must support all application requirements. And these requirements are getting more stringent as we care more about delays, more about reliability. And this is what has driven the cloud networks to put in these points of presence to meet these more stringent requirements. But it's exactly this dual role that L3 plays that prevents change. The network must meet additional application requirements, but the only layer that can address those requirements is exactly the layer that can't be changed. That's the paradox of the current internet architecture. And what's a sad irony that it's the only layer that can't be changed. So this is why the internet is hard to change. So when we turn to the second question and we say, how can we overcome this barrier? The hint is in that last line. Layer 3 is the only layer that can't change. And so the proposal that we talked about in the CCR paper is something we call the Extensible Internet. And it uses the current IP protocol infrastructure as is. So this is not proposing we throw things out, we put in something new. The current internet will continue to operate during this period, completely backwards compatible. But we do introduce a new network layer above L3. We call it the service layer, or L3.5. And it offers these in-network services to host. It's like the current private networks, but more general. We're talking things like pub/sub, or defense against denial of service, or doing private DNS lookups. And by putting in this extra layer, L3.5, what it does is it decouples L3's 2 roles. Currently, layer 3 is the interface to both L2 networks, so it must be the narrow waist, but it's also the interface to L4 on hosts, so it defines the internet service model. In EI, L3 is still the interface to L2 networks, but it does a good job. We don't need to change L3. But L3.5 is now the interface to L4. And notice, there's no reason for L3.5 to be narrow. It doesn't have to be the narrow ways. It can meet a wide range of needs. Nor is it every reason for it to be in every router, so it could be more easily deployed and changed. So we've split apart L3. And so what would this new internet look like? And I'll take most of my remaining time to describe it. So the service layer, it's implemented at service nodes, SNs. These are clusters or racks of servers deployed at the network edge, which just means they're close to clients. Every host is associated with one or more service nodes. The typical communication pattern is you go from a source to the service node associated with the source, to the service node associated with the destination, to the destination. All this stuff is tunneled over IP, so you're still using IP as the basic packet transport. And the source specifies which service to invoke at the service model. And that means that services need not be backwards compatible, that you can do much more than you can do in these current cloud private networks, because the client actually can manually invoke it. So you can do things like multicast. So this is just a picture. The only thing to take away here is whether you're in a home or office, whether you're on a cellular network or in a vehicle or in a cloud, there will be a service node nearby that help mediate the communications. Now, the key point here is that all the services are in software because they're running on servers. So standards are open source code. They're not written specifications. And the necessary software components are standardized service modules. For every service that you propose, there has to be some code implementing it. But that code is going to run in a standardized execution environment that has a few simple primitives, packet in, out, ephemeral storage, stable storage. But that environment is going to be a write once, run anywhere kind of environment. And then that environment has to run in some kind of runtime or orchestration that handles scale up, scale down, failing. And that doesn't have to be standardized, but there'll be open source versions of this available in Kubernetes and OpenStack and whatever. Now, these services, this isn't where you're going to run your machine learning job. These services involve limited computation, things like packet forwarding, payload processing, simple functions like caching. And these service nodes could have enclaves, secure enclaves, and hardware accelerators, and we hope that they do. And the way you choose these services, there's going to be a governance, much like IETF. It probably will be the IETF, which determines, what are the public services that everybody has to support, and that forms the new internet service model. And what's really the most radical change in this approach is the deployment model. Because the services are just an approved software module, it's actually an implementation. It's easily deployable in all the service nodes because it runs in this write once, run anywhere execution environment. So there's no per vendor, per domain deployment decision process that makes it very hard to roll things out. So this is an internet with a universal but growing waistline, which is why I identify it with it. Now, the kinds of potential services we're talking about are things like, the basics of flow termination, caching, and load balancing, support for other delivery models like multicast and pub sub, redirection and QoS, meaning more like the SD-WAN QoS of picking the best links. I think one of the huge impacts this approach could have is improving security and privacy. That is, the presence of these secure enclaves and the like will allow protection against DDoS, the ability to attest when you're talking to a server that you can have a proof that the software on that server is what you think it is, ODNS-like and Tor-like privacy mechanisms, and support for new architectures. If you want ICN, you write a service module, and if the IETF or whatever approves it, you can just roll it out. This isn't about replacing all the routers in the world. So remember that the goal of the extensible internet is to produce an architecturally clean version of what the cloud private networks are doing. And because it's architecturally clean, it can be more fully extensible because the clients can actively invoke the services they want. And it becomes more evenly distributed. It becomes part of the public internet. And it enables it to be the future internet but in a fully backwards compatible way. Nothing breaks. When this rolls out, anything that just wants to use the normal internet, nothing breaks. So I now want to get to this key question that, given the failures of what we've tried to do in the past and have failed, why is now different? Because I find when I talk to researchers, you say new architecture and their eyes just glaze over. And they look at me with this look of pity, like, Scott, you still believe this is possible? You know, I feel badly for you. So let me tell you why I believe it's possible. Because fear is a great motivator. The internet architecture has resisted change. And we have many explanations for why it's resisted change. I've given one here. But the truth is, there has never been an alternative. There is now the private clouds network. They are giving their customers better service. That is, things that are deployed in clouds get better network service than if they're deployed just on some random site. So they are a competitive pressure. And the clouds could easily reduce the public internet to primarily the last mile. Several speakers here have already spoken about that implicitly, as that's the way the world is going. This is clearly their plan, that, you know, as soon as your packet hits central office, it leaves and never comes back. So the internet's choice, and by here I mean the public internet's choice, is change or shrivel. And the extensible internet is one possible change that will preserve the internet's role by providing a network infrastructure that is as featureful as anything the clouds are rolling out. And with that, I thank you for your attention. I welcome your questions. And if you're interested in participating in this effort, please contact me. So thank you.
Thank you, Scott. Wendy, any questions in the chat session for Scott?
Yes, there is. That's one question. How lean the edge will affect L3? Or how can you see the edge in terms of service layer?
So I think that the edge, first of all, the service layer, these service nodes are at the edge. And so I think there's going to be a very strong symbiotic relationship between the edge as a place to do computing and the edge where these services are deployed. And so it's true that you're not going to run your machine learning tasks in EI, but for instance, I think the way you are going to find your edge computing nodes will probably be through a redirection service in EI. And there are simple things you can do, simple queries, simple other processing which would happen. One of the statements that I've heard from hyperscalers is the closer you get to the edge, the more expensive compute becomes. And so we think of EI as doing very simple compute that can push much farther out to the edge, and that the more complicated, the more long-term tasks that you're doing. Remember that if you're pushing out to the edge in order to get rid of speed of light delays, then the computation you're doing better be really, really short, or else it's not saving you much time. And so we think that the services can provide some of that, and then other things that are more longer lasting will go to the edge, but maybe the edge doesn't have to be placed at such an expensive place. It can be a little further away.
Okay.
There's one more question, if we have time for one more question.
Sure, let's go ahead.
Okay, many similar proposals existing, like CFN, APN, diecast, etc., are using the concept of mapping agent service nodes at edge in order to get a good deployment model. So what is the major difference or main advantage of EI from them?
Well, I mean, actually, the main advantage is all this is built into a network. There is, why would you do caching in EI? You can do it in CDNs. Why would you do other kinds of load balancing? You can buy load balancing services. But what made the internet great was that you didn't have to go out and buy a bunch of special services in order to throw together a network. And so what EI is trying to do is provide these services in a single platform where once you buy your internet services, these come for free. And that is going to be where the explosion of creativity comes from. Whereas right now, if you're going to deploy a service, you have to go to the clouds, you have to go to these other things, Fastly, that Cloudflare, that provide the service because you can't get it from the public internet. So that's why it's not that we're going to, this particular service, we're not going to do things that other people can't do. We're going to just do it in a way